Okay, we're getting into our next chapter, and the unit has to do with polynomials, as I mentioned yesterday. This unit is a little bit different because we really concentrate on only a few things, but we take them into more depth, as opposed to what we've seen in the last few chapters where we went over a lot of different topics. So our goal for this unit is to be able to graph cubic, quartic, and quintic polynomials. Those would be degree 3, 4, and 5. And our major emphasis is going to be finding the roots. And the roots that are real are the x-intercepts. We talked about that a little bit yesterday with quadratics. And our strategy is going to be use what we know about quadratics to help us generalize to other polynomials. Okay, so for our notes today, which are notes number 17, we're going to be looking at a way to find roots and to make rough sketches of polynomial functions. And what I'm going to do is first do an example for you to watch, and that's going to be a quadratic, and then we'll use those ideas and do an example together that is not quadratic. So finding roots, just watching. Here's a quadratic function, and what we would do, remember that to find the roots is to find the points that have a y coordinate of 0. So we would set the y, or the f of x, equal to 0 and solve this equation. And this equation happens to be factorable. So we're going to factor the right side into x minus 3 times x minus 2. And then using the zero product property, we set each factor equal to 0 and solve each equation. We get x equals 3 or x equals 2. So then for the roots, we would say that they are x equals 3 and x equals 2. And in terms of the linear factors, linear meaning x to the first power, and factors we had up here, we would say that those are x minus 3 and x minus 2. Not every problem can be factored, so not everything's going to have linear factors. So the technique that was used in that example is factoring. So let's see if we can apply that idea to the non-quadratic function. So here is h of x equals x cubed minus 4x. And I'm still looking for x-intercepts, so I want to start by finding the roots. Let h of x equal 0. Now, what we did last time was factor, and this is factorable. We can start by factoring x out of both terms. That's our greatest common factor. And then we have a difference of squares, x squared minus 4. So let's factor that into x plus 2 times x minus 2. And now we can set each of these factors equal to 0 and solve each one. So we have x equals 0, x equals negative 2, x equals positive 2. So those are the roots, 0 and plus or minus 2. And then the linear factors are x and x plus 2 and x minus 2. Okay, so it's not always going to be possible to factor, but when it is, that's a great technique for finding the x-intercepts of a cubic function or any other function. Okay, let's try another one. Still working on finding roots. And this time we have k of x, and this is not factorable. We still need to start by setting it equal to 0. So we're going to either complete the square or use the quadratic formula. Most people elect to use the quadratic formula. So we have x equals the opposite of b over 2a plus or minus the square root of b squared minus 4ac all over 2a. So we get 3 halves plus or minus the square root of 21 over 2. Now, these are real, so they are x-intercepts, but they're not rational. That's okay. They could still be graphed if we were graphing the function. We can still list them as roots. If you were graphing, you would approximate these. You would put these in your calculator. We don't have linear factors because we weren't able to factor it. Okay, so let's see. Our technique there was quadratic formula. So here's our example of a cubic function, m of x. Now it's cubic, not quadratic, so it doesn't make sense to jump to the quadratic formula right away. However, We're still going to start by setting it equal to 0. Notice that all the terms have a factor of x, so we can start by using the factoring technique. Factor the x out, set each factor equal to 0. We have a linear factor and we have a quadratic factor. The quadratic factor is not factorable, so we're going to use the quadratic formula to solve that second one. The opposite of b over 2a plus or minus the square root of b squared minus 4ac over 2a. So we have 3/2 plus or minus the square root of 17 over 2. Okay, those are real, so they could be graphed as x-intercepts. They're not rational. We don't have a bunch of linear factors. We do have just x as a linear factor, but the other factor was quadratic. And the roots are 0, so don't forget about the one we found earlier. 0, and then also 3/2 plus or minus square root 17 over 2. Okay, we have a bonus in this problem. Notice it says make a rough sketch. And so what we want to do for a rough sketch, and I mean this is really quite rough, we want to approximate where those x-intercepts are. So let's find the approximate values of those numbers. Okay, so 3/2 plus square root 17 over 2 is approximately 3.6, and 3/2 minus square root 17 over 2 is approximately negative 0.6. So we'll just go by ones. And then we can plot these roots, these x-intercepts. We have one at 0, one at negative 0.6, and one at 3.6. And then it's going to make sense that the graph either does something like this to go through those points, or perhaps it does something like this. So how are we going to figure out which way it goes? One thing we could do is find one more point. So what if we substituted 1 in there for x? We would get 1 cubed minus 3 times 1 squared minus 2 times 1. So we have 1 minus 3 minus 2. We have negative 4. So we have the point 1, negative 4. Now for future problems, we are going to learn how to figure out which direction the graph goes without needing to plot more points. So that was just for today, basically. We have this point way down here. So that helps us know that we should do something like this. That's a pretty rough sketch. We don't really know how high to go, how low to go, where to turn around, but it gives us an idea of the shape of the graph. Okay, we're going to do a few more examples of roots and rough sketches. And this one happens to be a quartic polynomial because it's x to the 4th as the highest power. Now we have seen some factoring of quartic polynomials before. We treated them as quadratics in some cases. Remember, I called them quadratics in disguise. And of course we're going to start out by setting it equal to 0 if we're looking for the roots. And then we can factor this into x squared minus 2 times x squared minus 5. We can set each factor equal to 0. Now, these aren't factorable any further, so we're not going to get it down to linear factors. However, each of these equations can be solved using the square rooting method. So if we add 2 to both sides and then square root both sides, we have x equals plus or minus square root 2. And then for the other one, we're going to add 5 to both sides and square root both sides, and we have x equals plus or minus square root 5. So those are the roots. Now for the rough sketch, the square root of 2 is approximately 1.4, and the square root of 5 is approximately 2.2. So suppose we go by ones like this. Now if you look back at the equation and you put 0 in for x, you're going to get 10. So we know the y-intercept is the point 0, 10. So let's use that as an extra point. And we have our roots at 1.4, 2.2, negative 1.4, and negative 2.2. So it's going to do something like this. It makes kind of a W. Once again, this is pretty rough. I don't know exactly how high it goes, how low it goes. Just know the general shape is like a W. It opens up, and just like a parabola would open up if it had a positive leading coefficient, notice that this has a positive leading coefficient of 1, and it opens up. So that trend is going to continue. Okay, let's do this one. This one is quintic because you have a 5th power. So just like quintuplets would be 5 babies, quintic means x to the 5th is the highest power. Let's find the roots. So we're going to set it equal to 0. We can factor an x out of all of the terms. And the remaining quadratic is, or the remaining quartic, I should say, the x to the 4th is quartic, is a quadratic in disguise, meaning I could factor it like I would factor a quadratic, x squared minus 3, x squared minus 2. So we can set each of these equal to 0 and solve each one. So we get x equals 0, that's one of our roots. We're going to solve by square rooting. We get x equals plus or minus square root 3, 2 more roots. And then x equals plus or minus square root 2, 2 more roots. Remember, those are approximately 1.4, and the square root of 3 is approximately 1.7. So let's do our rough sketch. We have the roots at 0, 1.4, 1.7, negative 1.4, negative 1.7. Let's see, how about an extra point? If I put 1 in there, I get 1 to the 5th minus 5 times 1 cubed plus 6 times 1. So 1 minus 5 plus 6. That is 2. So that's going to be up here somewhere. Doesn't really matter how high we go. That's just going to help us know what to do to connect these points. Something like that. Notice that for this one, this 5th power polynomial, one end goes down, one end goes up, just like a line would have one end down and one end up. So that's a trend we're going to see with odd powers. Okay, so there's one more thing that I want to go over with you today, since that was a short lesson, just to prime us for tomorrow's lesson, which will probably be a little bit longer. So just to take a little bit of the pressure off of tomorrow, I'm going to go over something called polynomial division. Today we're going to look at long division, and then tomorrow I'm going to teach you a method called synthetic division. But let's go back to numerical long division. Let's say you had 21 and you had to divide it into 536, and you were going to just use paper and pencil and do long division. So you'd say to yourself, let's see, does 21 go into 5? No, I better move over 1. Does 21 go into 53? Why, yes, it does. How many times? 2. So you put a 2 up there. And then the next thing you do is you multiply the 2 by 21. So 2 times 21 is 42. You write it down and you subtract. What do we get when we subtract? We get 11. What do we do next? We bring down the next number. So now we have to ask ourselves, does 21 divide into 116? Well, sure it does, but how many times? You might guess 4 or 5 or 6 or something like that. It's 5 point something, so we put a 5 up there, and then we go through the process again. 5 times 21 is going to be 105, subtract, and we get 11. Now at this point, there's nothing more to bring down, so we choose either to write this as 25 remainder 11. That was kind of the elementary way of doing it. Another way to do it is to write your remainder as a fraction, so 25 and 11 21sts, or to just put a decimal point, put some zeros, and keep going. So the method that's going to apply to polynomials is going to be to write your remainder as a fraction. So we're going to apply this to polynomials, which means this kind of problem. Let's say I have x minus 2, and I'm dividing it into 3x cubed minus 2x squared plus x minus 4. I don't know how nicely this is going to go in because I just made that up. So what we do is we say to ourselves, does x divide into 3x cubed? Why, yes, it does. So x times what is 3x cubed? It would have to be x times 3x squared to give us 3x cubed. Now, once we write the 3x squared up there, we multiply it by both of these and we write it down. So 3x squared times x is 3x cubed minus 3x squared times 2 is 6x squared. And remember what we did over here after we wrote it down? We subtracted. So we're going to subtract. I like parentheses around it to remind me to distribute the minus. So 3x cubed minus 3x cubed is 0. Negative 2x squared minus negative 6x squared is 4x squared. You write it down and you bring down the next one. Then you go through it again. So does x divide into 4x squared? Why, yes, it does. X times what would be 4x squared? It would be x times 4x. So that goes up there. And then the 4x gets multiplied by both of those. So 4x times x is 4x squared. 4x times negative 2 is minus 8x. And then we're going to subtract that whole thing. And when we subtract, we end up with 9x. There's one more to bring down, so we bring down the next one. And we repeat the process. Does x go into 9x? Well, yes, it does. It goes in there 9 times. So we put a plus 9. And then we multiply the 9 by the x. And we multiply the 9 by the negative 2. And we subtract that whole thing. And that gives us 14. Now there's nothing more to bring down, so 14 is the remainder. So we write it like this, plus 14 over x minus 2. And that is polynomial long division. It is long in time and it is long in space. We don't have to spend a lot of time on it because next time I'm showing you the shortcut for it, but you need to see the background before you're ready for the shortcut. I hope you don't mind if you have a short assignment today, speaking of short. So I just have 3 problems for you to do. I want you to find the roots and make a rough sketch for these 2 polynomials, and then I want you to practice the long division on number 3. Thanks, everybody.